Hello everyone. In the previous video, I have shown you how the Smith chart. You can take a look at the right hand side here is conformally mapped from familiar rectangular impedance coordinate onto a polar plane. Essentially, the reactive or the vertical axis has been bent around in such a way that plus and minus infinity is included within the boundary of the chart. Another key point to highlight is that the lump element movements on the Smith chart, which form the basis for impedance matching and build a foundation for the circuit design. In this video, I am going to demonstrate to you using FIPA EDS software. So here I have launched it, and you can see on the left hand side are the list of the element categories. I have the first one is a lump element. Now I can drag the port in. It is a 50 ohm by default, and then I will bring in the resistor. Let's make it as variable R. So I make a connection from here. I would like to see this in the Smith chart, so I have chosen, by default it is S parameters, so you can choose Smith chart here. So before the plot, you can select S parameters, and then I can plot it. So you can see that because this is the value of it is equal to 1, then it is very small impedance. So it would be at the left hand side, which is the short circuit position. Now let me try to tune this and make the maximum of it to be 1000, and then the step side to be 10. So now you can see if I increase the value of resistance, it will move to the right hand side, which verify that the right hand side is the open circuit position. So if the value becomes smaller, it will be this side. And if it is 50, which is the value the same as this, it will be equal to 1 normalized, and the value of your S parameter is almost 0, or it's 0 because it's matched. This is 2.5 10 to the power minus 9. So this is very, very, very small. So there's no reflection here. So what you can see is that when I move or I change the value of this resistor, it would only move along the real axis. Now if I add an inductor, and I can make the value of my resistor to be 25, so that it will move to this side, is bigger, and then I can, it will show some error because I haven't key in the value of L, so I put this is to be L nanohenry, and then make it 10 nanohenry. So when I see the response, you see it go up, right? So this is the inductive region. When I change this to an to a capacitor, so a capacitor, and make it as, say, C, and in picofarad. So I make C to be 10, so it's 10 picofarad. So the point now has been moved to the lower side. So this is the capacitive region, and the upper half is the inductive region, and the real axis is the resistive when this is equal to 0. Okay, another key point that I want to show. So you already got the familiar of this. So the left hand side is short circuit, right hand side is open circuit, top is inductive, down capacitive. Now let me try to add another element to show you the lump element movement. So if I add an inductor that of the value L, right? So before I do it, let me show you where is the point that we plot here. So the point is at this location, is at 0.5 minus 0.637. So now if I add an inductor, the point will move up, right, from our observation previously. So let me make it just to be equal to 1. Then I plot. So you can see where's the point. I think this is too small. I need to make it, no, sorry, it's too large because of the inductor is in Henry. I need to make it in nano. Our range operation is, the operating frequency is 500 megahertz. So here, let me show you once again. Okay, so it was, oops, what is the error here? Oh, I haven't select the parameters I want to see. So I select S11 and then I click, so it's here. Now I add this inductor in, then I plot again. So you see that the point has moved up, right? So let me choose this inductor element, make the value of this to be 100, make it bigger, and the step up to 1. So if I increase the value, you see it move up, right? This is the clockwise direction. Now, if I have already reached here and then I want to bring it down here, so what I need to use is a capacitor, because capacitor will bring it counterclockwise. That's what we have understood from the previous video. So now it was here, then when I add a capacitor, so you can see it has been moved from here to here down further. And the same thing happened when we do the shunt element, right? For shunt element, if it is a capacitor, it will move down, and move down means it will move clockwise, and if it is inductor, it will move counterclockwise. So capacitor clockwise, inductor is counterclockwise. So now I make it as a P, C in picofarad. And before I plot this, let me show you the one without this first, and where is the point. So now the point is here, and when I add a capacitor, so it will move clockwise, right? It will move clockwise, and because this is a shunt element, it will move along the admittance circle, not the resistance circle. So the movement will be like this. Let me plot this for you, and you can see it move here. And the same thing happened to the inductor. It will move to the other way around. Okay, now after having understood these two concepts using the software, I'm going to show you how we can use this to match a complex impedance to the a real source, right? So now I have here is a 200 ohm resistance. So maybe I make this R to be 200 here. And I have a capacitance of reactant value minus J100. And in this software, we have this element called FIR, frequency invariant reactance. So you don't need to calculate the capacitance value to get minus 100. So you can just put this minus 100 J here. Now let me plot where is it. And it is mapped to 100 ohms. So I can plot and see the point is at here. You see, this is 200 minus J100. So it's normalized by 100 is 2 minus J1. Now I know that no matter if I add the series element, it will move up or down, and the resistance value remains 2. So I have to add the shunt element. So I want to move it here or there. So if I want to move down, I need to use the capacitor, because capacitor will bring it down. Now let me show you that I will use this capacitor C and then in picofarad, and then maybe I make it equal to let's say 1. No, doesn't matter. We can start first. So you can see that it will move down. So here it was, and then now we go. Yes. So our objective is that to move until the real part become 1. So I have moved too much, so I have to tune it back. So now I tune it back to, let's make it less, so it's like 1.018. Now I can, if I decrease further, it's like 1.1. If I increase, it's 1.018, right? It will be a bit too much, right? So I need to add a little bit, but if I add 1, it would go too far to the 0.945. If I decrease, it would go to the other side. Then I have to adjust my decimal point here. So I put the step size to be 0.01, so I can see. So you can see it's almost 1, right? You can try to adjust further, like maybe put 1 more, and then you go until you reach 1, all right? So you have already found the value of a capacitor, which is 0.923 picofarad, to move in clockwise direction from here to here. And how do we move from this point to 1? You see that it's going to be in the clockwise direction. So I need to use an inductor, because inductor will bring me there, right? So this is L, and then this, maybe I can put it 1 nanohenry. 1 nanohenry. So let me plot again. So you can see that it was from here, now it moved up, and I can show you together. Here we have, maybe I put the step size to be 1, and this is maybe 100, make it bigger first. So now I move, you see, it moved clockwise direction. So it move clockwise direction, and I have reached this position where my whereas my point is at the center, right? This is matched. I can verify this using the S parameter as well, and I change the frequency range maybe from, let's say, 400 to 600, and see the response. Yes, using S parameters. So you see that it's matched at 500. The value is minus 71 dB. Okay, now let me demonstrate to you using another element. Just now we use the capacitor, it will move in the clockwise. If I use an inductor, okay, let me bring back to the Smith chart, and then we can plot this again. Oops, I need to make my single point only. Let me make it like just now, 500 to 500, and then here is my point. Okay, now I just want to show you that because we don't have any frequency dependent element here, that's why we don't see the point. Now I make it just a single frequency, so it will show this point, and it is at 2 minus J1, and I want to bring it up to reach another side, right? It also would have the intersection of the unit circle equal to 1. So if I want to move counterclockwise, I have to use the inductor. So I bring an inductor here, and this is to be put as L, and then make it nanohenry, and maybe I put it as let's say 10, or I put it 50, maybe. Let's see, it's faster. So it will move because it's very far. So I put 50 nanohenry. You see how much it moved from here to there, right? So now I click plot. So you see, I almost reach because it's like 1.141. Okay, maybe I moved too much or too little, right? So I can decrease a bit. It's because it moves too much. All right, now I got 0.995. Or you can decrease the accuracy by changing the step size. Now I have moved here. How do we bring this point to here, which is in the counterclockwise direction, I have to use a capacitor. So now I have used the capacitor here. The value is equal to C in picofarad. Oops. Yes, is it correct? Picofarad, yes. And maybe I make it just equal to 1 first. So it was here, then it will move here, right? So now let me bring this to you. So it moved too much, then I have to adjust this value. So oops, I have to change this to maybe make it 5. Oh, maybe 3. Okay. So move further a bit. Move further a bit. Oops, here, right. It's equal to 2.61 picofarad. So we just add 2.61 picofarad, then it will move from here to here. So you can use, you can use the concept that we have demonstrated in terms of the lump element movements on the Smith chart to design any lump element matching as desired, right? So it's very straightforward. And what you need to remember is that when you add a series inductor, it will move clockwise direction. And if it is a shunt capacitor, it will be clockwise direction. So inductor, capacitor have a kind of a different direction effect, right? Clockwise and counterclockwise. So I hope you have learned something new today. Thank you very much, everyone.